All right, so today we're diving into something pretty fascinating.
Oh, yeah.
Yeah, Chow polynomials and augmented Chow polynomials
Yes.
and their connection to Schubert matroids. I know you're pretty deep into mathematics, so
I am.
this should be right up your alley.
Absolutely. I think you'll find this one particularly interesting.
Okay.
These polynomials are used in both algebraic geometry and combinatorics.
Wow.
And they have some really cool property. They're unimodal, palindromic, and gamma positive.
Okay.
Which is pretty remarkable in itself.
Right. And you know what really caught my eye was how these polynomials, especially in the context of uniform matroids, seem to have this unexpected link to Schubert matroids. What makes this connection so intriguing?
Well, before we jump into Schubert matroids,
okay,
it's worth highlighting that uniform matroids are thought to have the biggest Chow and augmented Chow polynomials.
Interesting.
Among other matroids with the same size and rank. And the paper we're looking at today actually unveils a brand new formula specifically for calculating these polynomials for uniform matroids.
So we've got this new tool to explore these potentially maximal polynomials.
Yep.
That definitely sounds like a big deal.
It is.
But before we get ahead of ourselves, let's rewind a bit.
Okay.
You mentioned R labelings earlier.
I did.
Can you remind me how those fit into the picture?
Absolutely. R labelings are crucial because they provide the framework for defining both the Chow polynomial and the augmented Chow polynomial.
Okay.
The beauty is that an R labeling always exists for the lattice of flats of a matroid.
So it's like the R labeling gives us a specific lens through which we can view and analyze the structure of the matroid.
Precisely.
And ultimately leading to these polynomials.
Exactly. Think of it as assigning, unique tags to each element in the lattice of flats. And this tagging system allows us to apply formulas like equations 3.1 and 3.2 from Stump's paper to calculate the Chow polynomial and the augmented Chow polynomial.
Now it's starting to click.
Good.
But you also mentioned multivariate versions of these polynomials.
Ah, yes.
What's the advantage of having those?
The multivariate Chow polynomial and its augmented counterpart are like enhanced versions of the standard polynomials. They offer a more...
So by introducing more variables, we're essentially gaining a finer resolution when examining these matroids.
Precisely.
That's really neat.
And if you want to go back to the standard polynomials from the multivariate versions, you just set all the variables equal to each other.
Interesting. So it's like zooming out from a detailed map to a broader view.
Yeah.
Okay. So the paper we're diving into today focuses on providing explicit formulas for these polynomials, specifically for uniform matroids, right?
Exactly.
And what's remarkable is that they present several different ways to represent these polynomials.
Yes.
For instance, equations 1.1, 1.2, and 1.3 all depict the Chow polynomial of a uniform matroid, but each uses a slightly different approach.
Yeah, different representation.
So it's like having multiple tools in your toolbox, each offering a unique perspective on the same problem.
Yeah.
That's quite elegant. And equations 1.4, 1.5, and 1.6 provide similar representations for the augmented Chow polynomial, correct?
Yes. And the beauty of having these multiple representations is that you can choose the one that best suits your needs.
Right.
Or the specific problem that you're tackling.
Okay, I'm really curious to see these formulas in action. Can we try them out on a specific example?
Absolutely. Let's take the uniform matroid.
Okay.
U sub 3005 sub.
All right.
If we plug it into each of the formulas in equations 1.1 through 1.6, we'll find that they all yield the same result for its Chow polynomial and augmented Chow polynomial.
Oh, that's fantastic.
It's a great way to demonstrate that these different representations, while appearing distinct, all capture the same underlying concept.
That's a fantastic way to build confidence in these formulas.
Right.
Seeing them converge to the same result is really compelling.
Absolutely.
Now let's shift gears a bit.
Okay.
And talk about these intriguing Schubert matroids.
Right.
Before we jump into definitions, can you give me a sneak peek into why there's this unexpected connection between them and Chow polynomials?
Well, what's remarkable is that the coefficients of these polynomials, which we've been discussing in the context of uniform matroids, actually count specific types of Schubert matroids.
Wow. That's mind-blowing.
It's like these abstract polynomials are encoding combinatorial information about these fascinating mathematical objects.
So we're not just dealing with abstract formulas here, we're uncovering a bridge
Exactly.
between seemingly disparate areas of mathematics before we get lost in the excitement. Can you give me a clear definition of Schubert matroids?
Of course. Schubert matroids, also known as nested matroids, generalized Catalan matroids, or shifted matroids.
Wow, that's a lot of names.
Are defined on a fixed ground set, say n, using a permutation of that set.
Okay.
They have some really interesting properties as described in Proposition 3.6 of the paper.
Okay.
Which delves into their loops, cogirth, and a fundamental property relating to their bases.
Okay, so we're talking about arrangements of elements from a set governed by a specific permutation.
Right.
And with these unique structural features like loops and cogirths.
Exactly.
It seems like Proposition 3.6 is laying the groundwork for understanding the anatomy of these Schubert matroids.
Precisely. And the connection to Chow polynomials is made even more explicit in Theorem 1.1, which you can find in Hoster's work.
All right.
It elegantly demonstrates that the coefficients of these polynomials for uniform matroids actually enumerate specific types of Schubert matroids.
It's like these polynomials are a secret code book.
Yeah.
For understanding the structure of Schubert matroids.
That's a good way to put it, yeah.
And you mentioned that this theorem builds upon two earlier discoveries.
Yes. One by Hampe, which linked the Chow polynomial of the Boolean matroid to the 8-vector of the permutahedron, which is the nth Eulerian polynomial. This result essentially showed that the nth Eulerian number counts the number of loopless Schubert matroids on any elements with rank.
So we're seeing how these seemingly disparate areas of mathematics, Eulerian polynomials, Boolean matroids, and Schubert matroids are all intricately woven together.
Exactly.
And what about the second discovery you mentioned?
That one was by Mier, and Larson.
Okay.
They demonstrated that the augmented Chow polynomial of the Boolean matroid corresponds to the h-vector of the stellahedron, which is the nth binomial Eulerian polynomial.
Okay.
This finding revealed that the coefficients of this polynomial count Schubert matroids of a particular rank without the restriction of being loopless.
Fascinating. It's like these earlier discoveries laid the foundation for the more general connection unveiled in Theorem 1.1.
Exactly, yeah.
But before we dive deeper into that, can we unpack Theorem 3.7 a bit?
Okay.
It seems to offer a concrete way to count Schubert matroids based on their rank, number of loops, and cogirth.
It does, yeah.
Can you walk me through that formula?
Certainly. Theorem 3.7 provides a formula for calculating the number of Schubert matroids with the given rank, number of loops, and cogirth. The formula might look a bit daunting at first, but it's beautifully structured.
Okay.
It involves summing certain multinomial coefficients over specific subsets, essentially partitioning the set of all Schubert matroids.
So it's like we're using these multinomial coefficients as building blocks to construct this counting formula.
Exactly.
Can you break down what each part of the formula represents?
Of course. The formula essentially utilizes multinomial coefficients, denoted as binum k1, k2, 0 to arido n, where the cores represent the sizes of the subsets partitioning the set of n elements. In this context, these subsets correspond to specific structural features of the Schubert matroids, namely their rank, number of loops, and cogirth.
So the formula is cleverly leveraging the properties of multinomial coefficients to count these Schubert matroids based on their specific structural attributes?
Exactly.
That's incredibly clever.
It's like a powerful lens that allows us to see the intricate organization within this seemingly complex collection of matroids.
This is amazing. But I'm also curious about Corollary 1.7.
Okay.
It seems to connect the Chow polynomials of uniform matroids to something called derangement polynomials and Eulerian polynomials.
Absolutely. Corollary 1.7 highlights a beautiful connection between the Chow polynomial and augmented Chow polynomial of uniform matroids with derangement polynomials and Eulerian polynomials, respectively. Derangement polynomials deal with permutations where no element stays in its original position, while Eulerian polynomials, as we discussed earlier, are related to the number of descents in permutations.
So it's like these derangements in Eulerian polynomials are capturing specific permutation patterns.
That's an excellent way to put it.
That are somehow embedded within the Chow polynomials of uniform matroids.
Yeah. this connection further emphasizes the deep relationship between combinatorics and the study of these seemingly abstract polynomials.
This is really fascinating.
It is.
But I'm also wondering about the coefficients of the Chow polynomials for an arbitrary loopless matroid.
Okay.
Are there any bounds or relationships to the uniform matroid case?
That's a great question. Ferroni and his collaborators proved a remarkable result.
Okay.
The coefficients of the Chow polynomial and augmented Chow polynomial for any loopless matroid are bounded by the corresponding coefficients in the uniform matroid case.
So the uniform matroid acts as a sort of maximal case when it comes to these coefficient values.
Exactly.
That's a really neat result. It definitely highlights the special role uniform matroids play in this whole theory.
Yeah.
But before we delve deeper into that, let's take a quick break.
Okay.
We'll be back shortly to continue exploring these fascinating connections.
Sounds good.
Okay, so we've established that uniform matroids hold this special place in the world of Chow polynomials and their connection to Schubert matroids.
Right.
What else can we learn about the coefficients of these polynomials?
Well, one thing that's particularly intriguing is that we can actually compute some of these coefficients explicitly.
Oh, okay.
For instance, if we look at the coefficients of the linear term x in both the Chow polynomial and the augmented Chow polynomial, we can express them using, neat formulas involving sums of binomial coefficients.
So we're talking about the coefficients 2 on k, right?
Exactly.
The notation kind of reminds me of binomial coefficients. So
it should, yes.
I'm not surprised they show up in the formula.
And what's really remarkable is that these sequences of coefficients, arXiv for a fixed k, have been studied before and actually appear in the online encyclopedia of integer sequences.
Oh, wow.
For example, when k is 3, we get the sequence A000125, and for k is 6, it's A008859.
Wow, that's fascinating.
It's like these coefficients have a life of their own in the broader world of integer sequences.
Like these seemingly niche mathematical objects are part of a much larger interconnected network.
Exactly.
I'm always amazed by how different areas of math seem to converge in these unexpected ways.
And in the non-augmented case, the connection goes even deeper. We encounter a special type of permutation called Grassmannian permutations. These permutations have at most one descent, meaning their values mostly increase as you read them from left to right.
So they're like almost sorted permutations with just a slight dip somewhere along the way.
And Corollary 3.9 states that CK, Hebe A2, actually counts the number of Grassmannian permutations of length n that avoid a particular pattern specified by a permutation sigma dollar in Sika with exactly one descent.
Wow. So we're counting these special permutations that have this restricted structure and avoid a specific pattern. It's like these coefficients are capturing some very intricate combinatorial properties.
And as you might expect, the sequences for the non-augmented case, ANT for fixed k, are also listed in the OEIS. For example, when k is 3, it's A000124. For k is 4, it's A050407. For k is 5, it's A050407.
Wow.
And for k is 6, it's A362193.
So many connections to known integer sequences. It really emphasizes how fundamental these coefficients are.
It does, yeah.
It makes me wonder if we could find similar interpretations for higher order coefficients like CK or tilde.
That's a great question. The formulas for higher order coefficients do get a bit more complex. But the key is that they still involve sums of multinomial coefficients. This strongly suggests they're also counting some combinatorial objects or patterns.
Interesting.
But the challenge is to figure out precisely what they're counting.
That sounds like a fascinating open problem ripe for exploration. Imagine unlocking a combinatorial secrets hidden within these higher order coefficients. You could reveal even deeper connections between these polynomials and the worlds of permutations, matroids, and integer sequences.
Definitely.
Absolutely. Speaking of exciting, there's one more result I want to touch on before we wrap up this part of our deep dive. It involves the top-heavy conjecture for the Chow ring of matroids. Can you explain what that's all about?
Certainly. The top-heavy conjecture, as formulated by Braden, Mathern, Proudfoot, and Wang, essentially predicts a certain inequality regarding the coefficients
of the Chow polynomial of a matroid. To understand it, we need to define the degree sequence of a matroid.
So the degree sequence is like a fingerprint of the matroid's structure.
For a loopless matroid M with ground set of size n and rank r, the degree sequence is given by $1 plus D1, 1 plus D2, 1 plus DR2, where D-doi represents the number of flats of M of rank I, 101M.
So it captures how the flats of the matroid are distributed across different ranks. That makes sense. Now, how does this degree sequence tie into the top-heavy conjecture?
The conjecture states that if $1 plus D1, 1 plus D-doi, 1 plus DR2 is the degree sequence of a loopless matroid M, and if the Chow polynomial of M is written as CHMQ CHUK, then the following inequality holds. CR physical for all Lino, air floor R2 or floor. In other words, the coefficients of the Chow polynomial are top-heavy, meaning the coefficients corresponding to higher powers of Q
are greater than or equal to those corresponding to lower powers of Q.
So the conjecture essentially predicts this certain symmetry or balance in the distribution of these coefficients.
And while the conjecture has been proven for certain classes of matroids, such as realizable matroids and matroids representable over a field of characteristic 0, it remains an open problem in general.
Wow. So there's still so much to explore in this area.
There is, yeah.
I can see why you're so fascinated by it.
Absolutely. There are always new connections to be discovered and new mysteries to unravel. And the beauty of it is that even seemingly abstract concepts like Chow polynomials can have these deep and unexpected connections to the world of combinatorics and concrete mathematical objects like matroids and permutations.
I completely agree. This has been an incredibly enlightening dive so far.
Good.
Let's take another short break and then come back for the final part of our exploration. I can't wait to see what other surprises await us.
Sounds good.
All right, we're back, ready to continue exploring this world of Chow polynomials, uniform matroids, and Schubert matroids.
Absolutely.
It's amazing how much ground we've covered. I feel like we're just getting started.
There's always more to discover. And actually, we can connect these polynomials to yet another interesting concept, the Kazhdan-Lustig polynomial. You might be familiar with them from representation theory.
I am, yeah.
But they have applications in combinatorics and geometry as well.
I'm familiar with them, but I wouldn't say I'm an expert. Can you remind me how these Kazhdan-Lustig polynomials fit into all of this?
Of course. The Kazhdan-Lustig polynomial, denoted as Q, is associated with a pair of elements in a Coxeter group. It's a polynomial with integer coefficients that plays a crucial role in understanding the representation theory of Coxeter groups.
I'm starting to remember. They're used to describe certain representations of Coxeter groups.
Exactly.
And they also have connections to the geometry of Schubert varieties. But how do they relate to matroids?
Well, the connection comes from the fact that the lattice of flats of a matroid actually forms a geometric lattice, which is a special type of posit that shares structural similarities with the Bruhat order on a Coxeter group.
Interesting. So we're saying there's an underlying structural similarity.
There is,
between matroids and Coxeter groups, which suggests we might be able to use tools from one area to study the other.
Exactly.
But how do Kazhdan-Lustig polynomials specifically enter the picture?
The key insight is that for certain matroids, namely those that are shellable, the coefficients of the Kazhdan-Lustig polynomial corresponding to the maximal element of the lattice of flats are related to the coefficients of the Chow polynomial of the matroid.
Whoa, that's a pretty deep connection. So we're saying that for shellable matroids, these Kazhdan-Lustig polynomials, which come from representation theory, can actually tell us something about the Chow polynomial.
That's right.
Which has its roots in algebraic geometry and combinatorics.
Precisely. It's another example of how seemingly disparate areas of mathematics can intertwine in these unexpected and beautiful ways.
This is really mind-blowing.
It is, yeah.
But before we get carried away with all these connections, I want to make sure
I
understand the concept of shellability.
Okay.
Can you give me a quick recap of what that means?
Of course.
In the context of matroids.
Shellability is a combinatorial property of simplicial complexes.
Okay.
And since the independence complex of a matroid is a simplicial complex, we can talk about shellable matroids. Essentially, a matroid is shellable if its independence complex can be built up in a specific way by adding facets, maximal independence sets, one at a time, such that at each step, the intersection of the newly added facet with the previous complex is pure and of codimension 1.
Okay, so it's like building a structure brick by brick, ensuring that each new brick is properly connected to the existing structure.
Yes, that's a great analogy.
And this shellability property is what allows us to connect the Kazdan-Lustig polynomial to the Chow polynomial.
Shellability provides a framework for relating those two polynomials. And it's proven to be a really powerful tool for studying the combinatorial and geometric properties of matroids.
This is incredible. I'm constantly amazed by the depth and interconnectedness of mathematics.
Me too.
It's truly fascinating.
But as much as I'd love to keep exploring all of these connections, I think we're nearing the end of our deep dive for today.
Okay.
Any final thoughts
or
key takeaways you'd like to leave our listeners with?
I think the biggest takeaway is that even in these seemingly abstract areas of mathematics,
there are often deep and unexpected connections to concrete combinatorial objects. In this case, we've seen how Chow polynomials, augmented Chow polynomials, and even Kazdan-Lustig polynomials can be linked to the structure and enumeration of matroids, particularly Schubert matroids. It's a beautiful reminder that mathematics is not just a collection of isolated formulas and theorems, but rather this tapestry of interconnected ideas waiting to be explored.
Absolutely. And for our listeners who are eager to delve deeper into this fascinating world, I would encourage you to check out the original source material that we've been discussing. The works of Hoster, Stump, Ferroni, Braden, Mathern, Proudfoot, and Wang all offer incredible insights into this exciting area of research.
Absolutely. And remember, the journey of mathematical exploration is never ending. There are always new connections to be discovered and new mysteries to unravel.
Couldn't agree more. It's been an absolute pleasure diving into this with you. Until next time, keep those mathematical synapses firing.
Indeed. Keep exploring and keep questioning.
Welcome back, everyone. We're going deep today, deep into proof as it relates to uniform matroids.
Always a good place to dive.
Okay. So we're using a research paper. It's called The Chow and Augmented Chow Polynomials of Uniform Matroids. Pretty dense stuff, but that's what we're here for. Lots of formulas all about those uniform matroids. And get this, there's this whole connection to something called Schubert matroids in this paper.
Yeah, it's pretty fascinating. It reveals some really cool things about how these mathematical objects are structured.
I can't wait. But before we really get into the paper, I was hoping we could level set for a sec. Can you remind us why uniform matroids are so important, like in the big picture of matroids? And maybe while you're at it, give us a quick refresher on what these Chow polynomials actually tell us, both the standard and augmented versions.
Sure thing. So uniform matroids, even though they seem kind of simple at first, they're actually really important because they're kind of like a benchmark for understanding more complex matroids, you know. In a uniform matroid, every subset of a certain size, they all form a basis, and that uniformity is really powerful.
So it's like the ideal case, in a way.
Exactly. Now, as for those Chow polynomials, think of them like mathematical fingerprints. We write it as Hood sub x, where m is our matroid. And the coefficients of that polynomial, they tell us how many flats there are of a given rank within that matroid.
And those flats are like those special subsets of the matroid, right? The ones that are like key to understanding the internal structure.
That's it. Think of them like subspaces within that matroid structure. And then there's the augmented Chow polynomial, written as sub m sub x. It's similar to the standard one, but it incorporates something called the augmented Chow ring.
Gotcha. And if I remember right, the coefficients of these Chow polynomials aren't just random numbers, right? They actually mean something specific about the matroid.
You got it. And that's a key point this paper is exploring. It turns out that when you're dealing with uniform matroids, the coefficients of their Chow polynomials, they're the maximum possible for any loopless matroid. So basically, uniform matroids are in this special position. Their structure seems to, like, maximize certain combinatorial objects that these coefficients count.
Wow, that's pretty amazing. Okay, so let's dig into this paper. Page 1, we have the abstract. Basically says that it's trying to, give us a better understanding of these Chow polynomials, focusing on uniform matroids. But it also mentions something that caught my eye, Schubert matroids.
Ah, yes, Schubert matroids. These are super important for what this paper's finding. Basically, a Schubert matroid is a matroid where its bases are determined by a specific permutation of its elements. Like, imagine you have a set of n elements. A Schubert matroid on that set, it takes a permutation of those n elements and uses that to decide which Kerrelment subsets are allowed to be bases.
So the permutation is like a set of rules for how bases can form within that Schubert matroid.
Exactly. Like, it introduces this hierarchy, among the elements. And only subsets that meet certain criteria based on that hierarchy can be bases.
Okay, starting to see how this works. And the abstract also says that this paper proves a conjecture by Ferroni. Adds a little mystery to our deep dive.
It's always fun to see a conjecture finally proven.
Right. Okay, moving on to page 2. The paper talks about some of the properties of these Chow polynomials. It says they're unimodal, palindromic, and positive. Can you break those down for us? Like, why are they important for this paper's argument?
Okay, so those terms. They describe specific characteristics of the polynomial's coefficients. Unimodal means the coefficients increase at first, then decrease, forming a single peak. Palindromic means they read the same backwards and forwards. And go positive. That refers to a particular way of expressing the polynomial using a special basis of polynomials called the gamma basis.
So these properties, they're not just like interesting on their own, right? They tell us something about the deeper structure of the Chow polynomial and how it relates to the underlying matroid.
Absolutely. They often hint at a nice combinatorial interpretation for those coefficients, which is what this paper is all about.
Makes sense. And then page 2 also briefly mentions those existing formulas by Hampe and Mier, and Larson.
Right. Those are like providing context for the new findings in this paper, showing how this research builds on what came before.
Yeah, it's all connected. Okay. So page 3, this is where things get really interesting. We've got theorem 1.1, that Ferroni conjecture we were talking about.
This is like the heart of the paper. It connects the coefficients of those Chow polynomials for a uniform matroid to the number of Schubert matroids that have specific properties. It's really beautiful.
It's saying that the coefficients give us a way to count specific kinds of Schubert matroids.
Exactly. And it's amazing that that connection even exists.
Right. Okay, so there's this notation in the theorem. It's called a multinomial coefficient, right? Looks a bit intimidating. Can you break it down for us?
It's not that bad, really. Think of it as a way to count how you can split a set of n things into subsets with specific sizes. The E part comes in when you pick a specific subset A, and you want to count partitions where the differences between consecutive elements in I determine the sizes of those subsets. It's like a way to be really specific about how you're dividing up the set.
Okay, so like if we had a set of, say, 6 things, and our subset was, I don't know, 2, 4, 6, how would we calculate that multinomial coefficient?
Great question. To calculate 6, 2, 4, 6, you'd break down 2, 4, 6 into maximal consecutive subsets, so 2, 4, 6. Then you look at the differences. 4, 2 equals 2, and 6, 4 equals 2, and that gives you the multinomial coefficient. 6, 2, 2, 2 equals 6, 2.2.2 equals 90.
Oh, wow. Okay, that makes more sense. And then the paper gives us example 1.6, which calculates the Chow polynomial of U sub 3005 sub in a bunch of different ways using those formulas from theorem 1.3. I guess that's to show us all the different sides of the theorem, right? How they all lead back to the same answer.
You got it. By calculating it in these different ways, it highlights how different approaches can converge, provides more evidence for the theorem. One method uses the multinomial coefficient formula, and the other two are based on counting permutations with specific descent patterns.
It's like seeing the same object from different angles. Okay, so ready to move on to page 4. All right, page 4, we've got R labeling. Looks pretty technical.
It is, a bit. But think of it this way. It's a way to add structure to what's called the lattice of flats of a matroid. Basically, the lattice of flats is like a diagram. It shows all the flats in a matroid and how they relate to each other, and R labeling. It assigns numbers to those lines connecting the flats in a way that, tells us about the matroid's structure.
So it's like we're adding signposts to help navigate this diagram.
Exactly. Makes it easier to understand how everything fits together. And then on this page, it looks like they're going over some basic matroid definitions, like a quick review.
Yeah, they mentioned ground set, bases, all that stuff. I guess they were assuming we already know that stuff.
Makes sense, right? This paper is definitely for people who are already familiar with matroid theory. Okay, so page 5. Now we're getting to the specifics of uniform and Schubert matroids. We touched on these earlier, but can you remind us what makes each one special?
Yeah, like what sets them apart?
Sure. So remember, uniform matroids are all about those k-element subsets being the bases. Any combo of k things from a set of n things can be a basis. Schubert matroids, though, they're all about that specific permutation. That permutation creates a ranking of the elements, and then the bases have to fit that ranking.
So permutation is like a filter. Only certain subsets can get through to be bases.
Exactly. Okay, page 6. Now we're getting into multivariate Chow polynomials. More variables. Why make things more complicated?
Yeah, what's the point of that?
Good question. Think of it like this. Regular Chow polynomials, they have one variable, x, that keeps track of the rank of the flats. But multivariate Chow polynomials have multiple variables, each one tracking a different aspect of the matroid structure.
Oh, so we get more detail.
Yeah. It's like using a more powerful microscope.
Yeah.
We can see things in the matroid that were hidden before, and they mention the Poincare extended ab index, too.
What's that about?
It's a more advanced topic, kind of beyond what we're doing today, but basically it connects these Chow polynomials to a bigger idea called graded posits, shows how different areas of math can be connected.
Always cool to see those connections. All right, pages 7 and 8. Here's where they start proving their main results. We don't have time to go through every single step, but maybe we could pick one lemma or something to see what kind of math they're using.
Good idea. Let's look at lemma 3.2. It's a good example of how they use R labelings and stuff about uniform matroids to prove something important.
Okay, what does this lemma actually say?
It says that there's a one-to-one correspondence between certain types of permutations called subset permutations and the R labelings of maximal chains in the lattice of flats for a uniform matroid.
Wait, subset permutation, what's that again?
Oh, right. It's just a permutation of a subset of the elements. So instead of shuffling all n elements, you pick some, maybe k of them, and shuffle those.
Got it. And how does the lemma connect these subset permutations to those R labelings?
Well, it says that the R labeling of a maximal chain, that's a chain going from the bottom to the top of the lattice, it can be represented by one of these subset permutations, but the permutation has to have a special property. The biggest element has to be in a certain spot so that all the elements smaller than it are included too.
So if my subset permutation has the number 5 in it, then it also has to have 1, 2, 3, and 4 for it to match an R labeling.
Yeah, exactly. And the proof is all about analyzing how R labelings are made and showing how they relate to these special subset permutations.
It's like all these abstract ideas are coming together.
Totally. It's like building a puzzle, you know? Every little piece fits together to make the whole picture.
All right, page 9. Looks like we're getting to the good stuff. Proposition 3.6. It seems like it tells us some important things about Schubert matroids.
Yeah, this one's about, like, identifying some key traits. It gives us a way to find the loops in a Schubert matroid and to figure out its cogirth.
Those terms again. Can you remind me, what are loops and cogirths in matroids? It's been a bit.
Sure. A loop is an element that's like all alone. It doesn't belong to any basis. And the cogirth is a little more complicated. It's the size of the smallest circuit in the dual matroid.
Okay, I think I need a refresher on dual matroids and circuits too, while we're at it.
No problem. Every matroid has this like mirror image called its dual. The bases of the dual matroid are the complements of the bases in the original matroid. So if a set's a basis in the original, all the elements not in that set make a basis in the dual.
So we just flip what a basis means.
Exactly. And a circuit is a minimally dependent set. It's dependent, but if you take anything out of it, it becomes independent.
So cogirth is telling us about those smallest dependent sets in the dual matroid. Got it. And this proposition, it lets us find the loops in the cogirth just by looking at the Schubert matroid's permutation and subset.
Yep. It gives us a way to get those properties straight from how the matroid's defined.
I bet knowing this stuff is going to be important for proving the main theorem.
Absolutely. That's where theorem 3.7 comes in. This is the big one. It gives us a formula to count how many Schubert matroids there are with a certain rank, number of loops, and cogirth.
Okay, I'm ready. What's the formula look like? Is it super complicated?
It's actually pretty elegant. It says that the number of Schubert matroids with those properties, rank Rs, loops, C cogirth, on a set of n elements, it's equal to a sum of those multinomial coefficients we talked about before.
Oh, those multinomial coefficients again. I guess they really are the stars of the show.
They are. Each part of the sum corresponds to a specific subset that fits those properties. And the multinomial coefficient for each term tells us how many different Schubert matroids we can make from that subset.
Wow. So we went from these abstract coefficients to actually counting these special matroids. This reminds me of that theorem 1.1, that conjecture by Ferroni. Are they connected?
Definitely. The paper shows that theorem 3.7 actually proves Ferroni's conjecture. Remember, theorem 1.1 said that the coefficients of the Chow polynomials for uniform matroids were connected to the number of Schubert matroids with certain properties. Well, now we have this formula to count those Schubert matroids, so that confirms the conjecture.
It all fits together. Amazing how we went from these polynomial coefficients to understanding these complicated matroids. Pretty cool.
It really is. Math is full of surprises.
Okay, pages 10 and 11. Looks like we're wrapping things up. There's a mention of corollary 1.7. What's that about?
That one highlights a connection between the Chow polynomials and two other polynomials. They're called the derangement polynomial and the Eulerian polynomial.
I remember those names from forever ago, but I definitely need a refresher.
So the derangement polynomial, it counts how many derangements of a set there are. A derangement is where you shuffle things up so that nothing ends up in its original spot.
Like shuffling a deck of cards so no card stays where it started?
Exactly. And the Eulerian polynomial counts permutations based on how many descents they have. A descent is when a number is bigger than the one after it in the permutation.
Okay, starting to come back to me. So how do those connect to the Chow polynomials?
Corollary 1.7 gives us a formula that writes the Chow polynomial as a sum involving those two polynomials. Just another example of how different parts of math can be related.
It shows how interconnected everything is. And to finish things off, we've got an open problem. I love those.
Yeah, the authors leave us with something to think about. They ask if there's a more general way to describe the coefficients of these Chow polynomials. In terms of counting certain permutations, lots more to explore.
It's never really over. There's always something new to discover.
That's what makes math so exciting. There's always more to learn.
Well, this has been an amazing deep dive. I feel like I've learned so much about matroids, especially the uniform and Schubert ones.
Me too. Glad we could do this together.
And thanks to everyone listening. We hope you enjoyed this deep dive into Chow polynomials and Schubert matroids. See you next time. Welcome back to the show. Today we've got a real treat. For those of you who love math, we're diving deep into the world of uniform matroids.
Oh, fun.
And their polynomials.
Excellent.
Now, I know many of you out there, you've probably already encountered these concepts before, but I think you'll be surprised at just how much beauty there is to uncover here. We've got some really exciting research papers that are exploring how a very special type of matroid, they're called Schubert matroids, can actually help us understand the coefficients of these polynomials.
Interesting.
So get ready, folks, because we're going to see some incredibly elegant formulas.
I love a good formula.
And some fascinating connections.
I love a good connection even more. It's always so exciting to see familiar mathematical concepts sort of appearing in a new light. And with this research on uniform matroids, that's exactly what we're doing.
Absolutely. So let's set the stage a little bit. We're dealing with uniform matroids, which are a simple but surprisingly deep type of matroid. They're denoted as UKN, where the ground set is the set of the first n positive integers. And the key characteristic here is that any subset of size k forms a base.
Exactly. Now, each of these uniform matroids, it has two very important polynomials associated with it. The Chow polynomial, which is denoted as AEN-EQX, and the augmented Chow polynomial, denoted as HENX. These polynomials, they're like unique fingerprints, encoding a ton of information about the matroid's structure. And what's really fascinating is that the coefficients of these polynomials, they turn out to be deeply connected to something that you wouldn't necessarily expect. Schubert matroids.
Schubert matroids. I mean, it's incredible how these seemingly unrelated concepts can be so intricately linked.
Right.
So how do we actually get from Schubert matroids to the coefficients of these polynomials?
That's the question. Well, it all comes down to a conjecture by Ferroni, which has now been proven to be a theorem. And it states that the coefficients of these polynomials can be understood by very carefully counting certain types of Schubert matroids.
Okay, so we're counting matroids.
We are counting matroids, but very specific ones.
All right, well, you've definitely piqued my curiosity.
Yeah.
So what kind of Schubert matroids are we talking about here? What makes them so special?
The theorem tells us that we need to focus on loopless Schubert matroids with a specific cogirth. Now, a loopless Schubert matroid essentially ensures that every single element in our set is part of at least one base. Cogirth, on the other hand, it refers to the size of the smallest dependent set in the dual matroid. You can think of it as a measure of how interconnected the elements of the matroid are.
Okay, so let me just make sure I'm following you here. We're saying that by counting loopless Schubert matroids with a specific cogirth, we can directly compute the coefficients of the Chow and augmented Chow polynomials for a given uniform matroid.
You got it. And what's even more remarkable is that we actually have explicit formulas to calculate these polynomials. Theorem 1.3 in the paper, for example, it presents 3 distinct formulas just for computing the Chow polynomial of UK nth.
3 different formulas. That sounds a little overwhelming. Could you maybe give us a taste of what those formulas look like?
Absolutely. One of the formulas, it relies on subsets of the set 1,
right.
And it makes use of these things called multinomial coefficients.
Multinomial coefficients.
Another formula, it focuses on non-consecutive subsets.
Okay.
And the number of permutations with specific descent sets.
Okay.
And then the third formula, it delves into the world of permutations and their descent sets, but in an even more intricate way. Now, each of these approaches, despite their differences, ultimately converges to the same result, which is pretty neat.
It's incredible how math can have these multiple pathways leading to the same truth. It's like a testament to the elegance and the interconnectedness of these ideas. But, beyond just seeing these formulas, I think what's really captivating is the why behind all this.
The why is always the most important part.
Why are Schubert matroids so fundamentally connected to the coefficients of these polynomials? What is it about them that makes this all work?
That's the million-dollar question. And at its heart, I think this connection boils down to the concept of independence in matroids. When we're counting these specific Schubert matroids, we're essentially capturing all the different ways that dependence relationships can arise within our uniform matroid.
So it's like each Schubert matroid, it represents a unique kind of fingerprint of dependence.
Yes.
And by meticulously counting all of them, we're sort of revealing the hidden patterns of dependence that are embedded within those polynomial coefficients. It's like those Schubert matroids, they're giving us a secret decoder ring for these polynomials.
That's a fantastic way to put it. It's like we're looking at the same underlying structure through different lenses, and these seemingly disparate concepts, they turn out to be 2 sides of the same coin.
Now, we've been focusing a lot on the Chow polynomial.
Right.
But what about the augmented Chow polynomial? Does it follow a similar pattern with the Schubert matroids?
It absolutely does. Theorem 1.4 in the paper, it offers analogous formulas for calculating the augmented Chow polynomial. And what's even more interesting is that these formulas can be generalized to a multivariate setting, which adds another layer of complexity and depth to this whole mathematical landscape. We'll delve into that in more detail a bit later.
That's exciting.
It is.
It's incredible how these seemingly simple concepts
right.
can lead to such rich and complex mathematical structures. It's like peeling back the layers of an onion
right.
and discovering more and more intricate patterns with each layer.
Absolutely. And speaking of intricate patterns, the paper also highlights another really fascinating connection. Expressing these polynomials in terms of derangement polynomials and Eulerian polynomials.
Ooh, those sound familiar. I remember encountering those in other areas of combinatorics. How do they tie into all of this?
Well, it turns out that both the Chow and the augmented Chow polynomials, they can actually be elegantly expressed in terms of these classical combinatorial objects. Corollary 1.7 in the paper really beautifully links these seemingly disparate concepts.
Okay, I'm all ears. How exactly do derangement and Eulerian polynomials enter the picture?
So the Chow polynomial can be represented as a sum of derangement polynomials, each multiplied by a specific geometric series. Similarly, the augmented Chow polynomial can be expressed in a comparable way, but using Eulerian polynomials. It really highlights just how interconnected these concepts truly are.
So it's like we're viewing the Chow and augmented Chow polynomials through the lens of these other well-established combinatorial objects.
It is.
And it's just incredible how these connections just keep popping up, revealing this underlying unity within mathematics.
That's what makes it so beautiful. It's like we're weaving together all these different threads of mathematical thought to create this more complete and stunning tapestry.
Okay, so amidst all this elegance,
yeah,
I'm also curious about the nitty-gritty details. How about we delve into those formulas for actually calculating the coefficients in these polynomials? The paper uses the notation key sub tem sub k, sum n tav, cn tavi 772, sub key n sub for the coefficients. Could you maybe walk us through an example, say for m will kill?
Sure. Let's take a look at C sub k n sub, which is the coefficient of excess in the Chow polynomial of UK and U. The formula, it involves a series of sums of multinomial coefficients. We start with 1, then we add a sum of binomial coefficients from I equal 3 to k1, and this represents a count of specific subsets. Then we add another sum of binomial coefficients, and finally a sum of trinomial coefficients. It looks a bit like this. See ever? 1 plus sum k1 ki3 plus sum k1 i3 plus sum k2 i3 plus sum k2 i3 plus sum k2 i3 plus sum k2 i3 plus sum kky.
I can see how this formula is systematically accounting for all the different ways that dependencies can emerge in our uniform matroid, which ultimately leads to that coefficient, the x feet set term in the Chow polynomial. But I can only imagine how much more complex these formulas must become as m increases.
You're absolutely right. The complexity definitely increases as m gets larger. And that actually brings us to a really fascinating open problem that's presented in the paper.
Ooh, an open problem. Mathematicians love a good challenge. What does this one entail?
The paper challenges us to find more intuitive ways to understand what these coefficients actually mean, possibly by connecting them to very specific sets of permutations. You see, we have the formulas, but they don't really paint a clear picture of what's happening combinatorially. It's like we've decoded the message, but we haven't quite grasped the language yet.
Yeah, though we can calculate the coefficients, but a deeper, more intuitive understanding is still out there, waiting to be discovered.
Exactly.
Like a treasure map leading to these hidden mathematical treasures.
I love that analogy. And unraveling this open problem, it could potentially reveal some truly profound connections between these coefficients and the world of permutations.
So we've explored these really intriguing connections between Schubert matroids, Chow polynomials, and even derangement and Eulerian polynomials. But I'm curious about how these results are actually proven. You mentioned using multivariate versions of these polynomials. Can you maybe elaborate on that a little bit?
Sure. So the proof relies on this clever technique involving multivariate polynomials. Instead of just using a single variable x, we actually introduce multiple variables, which allows us to capture more of the finer details of the matroid structure.
Okay.
So for example, instead of terms like x0 or x0, we might have terms like xx or xaa.
I see. So it's like we're adding more dimensions to our analysis, and that allows us to see patterns that might have been hidden in that single variable version.
Exactly.
But how do we construct these multivariate polynomials?
Yeah.
And how do they relate back to our original polynomials?
The construction of these multivariate polynomials involves something called an R labeling on the lattice of flats of the matroid. Think of the lattice of flats as this structured way to organize all the flats of a matroid, which are special subsets of the ground set.
Okay, got it. And what exactly is an R labeling, and how does it play a role in this construction?
An R labeling is a specific way to assign integers to the edges of this lattice, and these assignments have to satisfy certain properties. This labeling allows us to encode information about the descent sets of maximal chains in the lattice of flats.
Descent sets. Could you maybe unpack that a bit? What are those, and why are they important?
Sure. A maximal chain, you can think of it as a way to build up the matroid, starting from the empty set and going all the way to the full ground set. And as we add elements along this chain, the rank of the set might suddenly jump. And these jumps, those are what the descents capture.
So it's like we're creating this roadmap for exploring the matroid structure and the R labeling, along with these descent sets. They act as our guide.
That's a really great way to think about it. And the beauty of this approach is that once we prove the theorems for these multivariate polynomials, they automatically hold for the standard Chow and augmented Chow polynomials by simply setting all the variables equal to x. It's a really powerful technique because it helps reveal the underlying structure and connections in a much more profound way.
Right. So it's like we're proving a more general result that then encompasses the specific cases that we're really interested in.
Exactly.
And that's a testament to the elegance and power of mathematical abstraction.
Absolutely. By working in this more general setting, we actually gain a much deeper understanding of the underlying principles that are at play. It's like climbing a mountain to get a wider view of the entire landscape.
We've been focusing so much on uniform matroids and their polynomials, but you mentioned earlier that Schubert matroids are really crucial to understanding these coefficients. Can you maybe remind us what makes them so special and why they're so relevant in this context?
Yeah. Schubert matroids are a fascinating class of matroids that come from permutations.
Oh, wow.
Each Schubert matroid is defined by a permutation and a subset of its ground set. And they have this really beautiful geometric interpretation in terms of lattice paths.
Ooh, lattice paths. I always love when math gets visual. Can you tell me more about that?
Absolutely. Imagine a grid where you can only move up or to the right. A lattice path is just a path on this grid that starts at the bottom left corner and ends at the top right corner. Each Schubert matroid, it can actually be represented by a specific lattice path, and this visual representation gives us a powerful tool to understand their properties.
So there's like a visual aspect to these matroids, which is always really cool to see.
Yeah.
But how do these lattice paths actually connect to the coefficients of our polynomials?
The key here is that to understand the coefficients of those Chow and augmented Chow polynomials for uniform matroids, we have to count very specific types of Schubert matroids.
Okay.
And it turns out that characterizing these matroids by their number of loops and by their cogirth is really important for this counting process.
Okay, so we've touched upon loops and cogirth before, but I'd love a quick recap on why they're so important in this context.
Yeah, absolutely. So a loop in a matroid, remember, it's an element that's not part of any base. So when we're characterizing Schubert matroids, the number of loops helps us refine our counting based on this specific structural property.
Okay, that makes sense. And what about the cogirth? How does that help us categorize these Schubert matroids?
The cogirth of a matroid, as we discussed earlier, it's the size of the smallest dependent set in its dual matroid.
Right.
It's a measure of how interconnected the elements of the matroid are. So by considering Schubert matroids with specific cogirths, we're basically asking how many of these matroids require a certain minimum number of elements to create a dependency.
So by carefully counting these Schubert matroids with specific ranks, numbers of loops, and cogirths, we could start to unravel the mysteries that are hidden within the coefficients of the Chow and augmented Chow polynomials of uniform matroids.
Precisely.
It's just this beautiful interplay between different types of matroids, permutations, and polynomials.
It really highlights the interconnectedness of mathematical concepts. Exploring what seems like an isolated area can actually lead to these surprising and profound connections.
This deep dive has been a whirlwind of mathematical beauty and complexity.
It has.
But unfortunately, our time for this part is up. But don't worry, we'll continue our exploration in the final part of this episode, where we'll dive even deeper into the fascinating world of Schubert matroids and their connections to uniform matroid polynomials. So stay tuned.
I can't wait. So we were talking about how those polynomials can be expressed in terms of these other combinatorial objects.
Right, the derangement polynomials and the Eulerian polynomials.
Yeah, exactly. So it turns out that both the Chow polynomial and the augmented Chow polynomial can be written in terms of these classical combinatorial objects.
Oh, that's pretty neat.
It is. Corollary 1.7 in the paper, it beautifully links all of these concepts together.
Okay, so I got to ask, how do derangement polynomials and Eulerian polynomials even come into the picture here?
Well, the Chow polynomial can be represented as a sum of derangement polynomials, and each one of those is multiplied by a very specific geometric series. And similarly, the augmented Chow polynomial can be expressed in a similar way, but this time using Eulerian polynomials instead. It really highlights how interconnected these concepts are, even though they might seem totally different at first.
So it's like we're seeing these Chow and augmented Chow polynomials through a whole new lens.
Yeah.
The lens of these other, really well-established combinatorial objects.
It's like we're adding more tools to our mathematical toolbox.
Yeah. And it's amazing how these connections just keep popping up everywhere, revealing this underlying unity within mathematics.
Yeah.
Great. But amidst all this elegance, I'm curious about the nitty-gritty. What about those formulas for actually calculating the coefficients of these polynomials? I know the paper uses those notations, quote, sub k can sub and c tac check 772, sub cans. Could you walk us through an example maybe for m sub d?
Of course. So let's consider chi sub 2 sub che n sub, which is the coefficient of excedence in the Chow polynomial of UKM. This formula, it involves a bunch of sums of multinomial coefficients. It starts with 1, and then we add a sum of binomial coefficients from I equal 3 to k naught 1, which represents a count of very specific subsets. Then we add another sum of binomial coefficients, and lastly, a sum of trinomial coefficients. It looks a little something like this. CCKM 1 plus some K1I3 plus some K2I plus some K2I K2I O and LIKAN $2.
I see. So the formula is basically systematically accounting for all those different ways that dependencies can emerge in our uniform matroid. And that ultimately leads to the coefficient of the x-exit term in the Chow polynomial.
Exactly.
I can only imagine how complicated this gets as m increases, though.
You're telling me. As m gets larger, it gets really complex really fast. And actually, that brings us to this super fascinating open problem that's presented in the paper.
Oh, an open problem. That's exciting. What is it?
The paper basically challenges us to find a more intuitive way to understand what these coefficients actually mean, maybe by connecting them to specific sets of permutations. You see, we have those formulas, but they don't really give us a clear picture of what's going on combinatorially.
Right, so it's like we know how to calculate them, but we don't really understand their deeper meaning.
Exactly. It's like we've got the answer, but we don't know how we got there.
Yeah, it's like we've decoded the message, but we don't actually understand the language yet.
A perfect analogy. And solving this open problem, it could potentially reveal some really deep connections between these coefficients and the world of permutations.
Now, we've talked a lot about uniform matroids and Schubert matroids.
We have.
But how do we actually count these Schubert matroids? I know the paper uses the set I, 2, 3, 5, 7, 8 as an example, which they've partitioned into 2, 3, or 5.
That's a really good example to look at. So basically, what we're trying to do is figure out the size of the orbit of a Schubert matroid under a specific action of a group. We're working with the symmetric group SUM_SUB, which is just the set of all permutations of our ground set N. And the action, well, it involves permuting those elements of I.
So we're like shuffling around those elements in the set I, but how does that help us count the Schubert matroids?
So the key here is that the size of the orbit of that initial Schubert matroid, the one defined by I, and the identity permutation under this group action, well, it tells us exactly how many different Schubert matroids we can get just by permuting the elements of I.
So we're taking that initial Schubert matroid and creating a whole family of related matroids just by rearranging those elements.
Exactly. And the size of that family is actually given by a multinomial coefficient. In this case, it would be a Shimai, where AI represents the differences of the minima of those consecutive subsets in the partition of I.
Okay, I think I'm following. So for our example, would I 2, 3, 5, 7, 8, what would AB be?
So in this case, eta would be 1, 3, 2. We get that because the differences between the minima are 2, 1, then 5, 2 equals 3, and finally 7 to 5 equals 2.
So that multinomial coefficient is like this neat little package that captures the number of Schubert matroids we can create just by permuting the elements of 2, 3, 5, 7, 8.
Exactly. And it's amazing how this connects back to the world of matroids.
It really shows the elegance and the power of combinatorics. This connection between group actions, orbits, and multinomial coefficients, it gives us a deeper understanding of how those Schubert matroids are structured.
It's like we're piecing together a puzzle.
Yeah. This has been a truly incredible deep dive.
It has.
Into the world of uniform matroids with all their intricate polynomials and that surprising connection to Schubert matroids.
All right, who knew?
I feel like I've gained a whole new appreciation for the beauty and the interconnectedness of all these different mathematical concepts.
Me too. It's amazing how it all fits together. And don't forget, we still have that open problem to tackle. You know, finding a more intuitive way to think about those polynomial coefficients.
Oh, right. The mystery remains.
It does. Maybe it has something to do with specific sets of permutations. Who knows? But that's the beauty of math. There's always more to discover.
It's like a never-ending adventure. And with that thought, I think we'll wrap up this part of our deep dive. We'll pick up right where we left off in the final part of this episode, so stay tuned for even more exciting mathematical discoveries. All right, so before we wrap things up, I want to make sure we really understand how we count these Schubert matroids.
Sounds good to me.
We talked about loops and cogirth.
Right, those are key.
But how do those actually fit into this whole counting process?
So remember, a loop in a matroid, it's basically an element that's not part of any base.
Right, it's like a loner. It doesn't want to join the party.
Exactly. And when we're looking at those Schubert matroids, the number of loops helps us refine our counting, like we're narrowing things down.
Okay, that makes sense. And what about cogirth? How does that play into all of this?
Cogirth, if you remember, it tells us the size of the smallest dependent set in the dual matroid.
Right, it's like a measure of how connected everything is.
Exactly. So when we're looking at Schubert matroids with specific cogirths, we're basically asking, okay, how many of these matroids need a certain minimum number of elements before we can create a dependency?
So we're like setting these thresholds, these minimum requirements for dependence.
Right, and by carefully counting all those Schubert matroids with specific ranks, loops, and cogirths, we can start to unlock the secrets hidden within those coefficients of the Chow and augmented Chow polynomials.
It's amazing how all these pieces fit together, like this intricate puzzle.
It really is, and it highlights how connected all these different mathematical concepts are. Matroids, permutations, polynomials.
It's like we're seeing this grand unified theory of combinatorics.
You got it.
This deep dive has been a real eye-opener. I feel like I've learned so much about uniform matroids.
Me too. And it's great to see how much research is still being done in this area, like with that open problem we talked about.
Right, that challenge to find a more intuitive interpretation for those polynomial coefficients.
It's like a call to adventure for all those curious mathematicians out there.
Absolutely. Well, a huge thank you to you for guiding us through this incredible mathematical landscape.
It's been my pleasure. Really enjoyed it.
And to all of our listeners, we hope you enjoyed this journey as much as we did. Keep exploring, keep asking questions, and most importantly, keep that mathematical fire burning. All right, let's kick off another deep dive. Today we're tackling Chow polynomials, and get this, their connection to Schubert matroids. I mean, you know that Chow polynomials are super useful for understanding uniform matroids, but let's be real. Sometimes the math can be a bit much.
Yeah, for sure. I mean, they hold so much information, it can be hard to really grasp it all.
Right. But here's the cool part. Some new research has found a link between Chow polynomials and Schubert matroids.
It's pretty groundbreaking stuff, yeah. It shows there's a direct relationship between the coefficients of those polynomials and the number of Schubert matroids with certain properties.
So basically, if we study those Schubert matroids, we can unlock what's hidden in those polynomials.
Exactly.
Okay, so let's back up a bit first, just to make sure we're on the same page. You know about uniform matroids already, of course. Those are the ones where all bases have the same size.
Right, they're like a benchmark or something. We can compare other more complex matroids to them.
Perfect. Now, Schubert matroids, they've got these ties to lattice path matroids and all that. But their connection to Chow polynomials was, well, a mystery until recently.
That's where Ferroni's conjecture comes in. And it's been proven now, so it's a theorem.
Wow, a full-blown theorem. Okay, so to recap, we've got these two worlds, right? Chow polynomials on the one hand, and then we've got Schubert matroids. And Ferroni's work basically says they're not so separate after all.
Yeah. It's like discovering a secret passageway between two totally different rooms, right?
Uh-huh. I like that. So, how did Ferroni even figure this out? What does the theorem actually say?
So the theorem, it's theorem 1.1 in the paper, says that the coefficients of the Chow and augmented Chow polynomials for a uniform matroid are they're directly determined by the number of Schubert matroids with specific properties.
All right, let's break that down. What properties are we talking about here?
So there are three main ones: rank, loops, and cogirth.
Rank and loops, I get. Rank is the size of the bases, and loops are elements that aren't in any basis, but cogirth. It's been a minute.
Cogirth tells you how connected the elements of a matroid are. It's the size of the smallest circuit in the dual matroid. Basically, bigger cogirth means a looser structure, and smaller cogirth means things are tighter, more connected.
Gotcha. Thanks for the refresher. So Ferroni's theorem is saying that to figure out a coefficient in the Chow polynomial, all we have to do is count Schubert matroids with a specific rank, number of loops, and cogirth.
Exactly. It's pretty neat, right? Instead of all this algebra, we're just counting matroids.
It's a totally different way of looking at it. I love it. Before we get into the proof, though, can you remind me about the work by Hampe and and Larson? I know they laid some groundwork for this.
Oh, absolutely. They showed that the Chow polynomial of a Boolean matroid, which is a special kind of uniform matroid, is related to the augmented Chow polynomial. It's related to the augmenter of the stellahedron. Ferroni's theorem takes those results and makes them work for any uniform matroid.
Wow. So they had the pieces, and Ferroni figured out how to put them all together. Amazing.
Yeah, it's really cool.
Okay, I'm ready to dive into the proof now. How do we even begin to unpack something this complex?
Well, there are a few key steps. Introducing something called multivariate Chow polynomials. Then there's some tricky stuff with R labelings of matroid lattices. And of course, you have to go deep into the structure of those Schubert matroids.
Okay, hold on. Multivariate Chow polynomials. What are those?
Think of them like a souped-up version of regular Chow polynomials. We added more variables to break the problem down into smaller chunks. It's like taking a machine apart so you can see how all the pieces work.
Makes sense. And those R labelings in matroid lattices, those sound pretty abstract.
They are. But they give us a way to analyze matroids. Imagine a matroid lattice, like a diagram that shows you all the flats of a matroid. Then, with an R labeling, you assign labels from a set R to the edges of that lattice. It helps you capture how those flats are related. Then, if you combine those with subset permutations, Ferroni was able to connect the coefficients of the multivariate Chow polynomial to counts of Schubert matroids.
All right, so we're using these labels and permutations to bridge the gap between the polynomials and the Schubert matroids. It's like a Rosetta Stone or something.
Aha! That's a great way to put it.
Okay, so we've got these multivariate Chow polynomials, R labelings, matroid lattices, and we're trying to connect all of that back to the Schubert matroids and those three properties: rank, loops, and cogirth. My brain is already starting to hurt.
Haha, don't worry. That's all part of the fun.
Before we get lost in the details, though, I have to ask, what are the real-world applications of this? I mean, it's cool theoretically, but does it have any practical use?
That's a great question, and honestly, mathematicians are still working on that. The immediate applications might not be clear, but it could have an impact on things like optimization, coding theory, even network analysis. Matroids are used in so many different fields.
So understanding Chow polynomials better could help us with all sorts of real-world problems.
Exactly. It's all about uncovering the underlying patterns that control complex systems, and matroids are a powerful tool for that.
Okay, I'm hooked. Let's dive into that proof and see what Ferroni figured out.
Let's do it. You'll enjoy this, I think. Okay, so we've seen how Ferroni's theorem makes this connection between the coefficients of Chow polynomials and the properties of certain Schubert matroids. Now let's see how those properties, the rank, loops, and cogirth, actually show up in those Schubert matroids.
Okay, I think I'm ready to get into the weeds of Schubert matroids. What makes them so special? And how do we see those three properties in their structure?
So Schubert matroids, they're defined based on a subset, we'll call it day dollar, of the ground set. That's just all the elements in the matroid. We'll write that as non-k, meaning it's all the numbers from 1 to dollars. And then there's also a permutation of dollars, which we'll call $2.
Right. Like with a uniform matroid, we write 1k where I'm in the rank and then on the size of the ground set.
Exactly. So let's take a Schubert matroid. We can write it as that C. Now, if the Hab set dollar has size, dollars, then the Schubert matroid's rank is also dollars. So the size of dollars basically determines the rank.
Okay, so the rank is pretty straightforward. What about those loops? How do those fit into the definition?
Ah, the loops. So those are determined by both $dollar and the permutation by ball. Remember that the permutation mixes up the order of the elements. So the loops, they depend on the smallest element in the set $dollars, but according to the order given by dollars.
Wait, the smallest element according to the permutation. So it might not actually be the smallest number, right?
You got it. It's all about its position in the sequence defined by dollar. Let's say the smallest element in dollar, according to dollar, is written as high M, where dollar is some index. Then the loops of the Schubert matroid, that WR, are all the elements from chi M up to no, but we have to follow the order given by the permutation.
So we kind of rearrange the ground set based on pi, and then the loops are everything that comes before the smallest element of dollar in that rearranged order. That's pretty cool.
It is, and it shows you how important that permutation is. Now onto the cogirth. Remember, that tells us how connected everything is.
Yeah, smaller cogirth means more connections. Bigger cogirth means fewer. But how do we find the cogirth of a Schubert matroid?
So, like the loops, the cogirth also depends on both dollar and dollars. But this time, we look at the biggest element in other dollar. Again, according to the order given by $, say that biggest element is secchi. Then the cogirth of the Schubert matroid dollar is $1 plus 1 carrier, where noners is the size of the ground set.
Okay, so we've got the smallest element according to the permutation, determining the loops, and the biggest element according to the permutation, influencing the cogirth. It's all connected.
It is, and understanding how those properties come from the definition of a Schubert matroid is super important for Ferroni's theorem. Remember, it says those coefficients in the Chow polynomial, they're linked to the number of Schubert matroids with certain rank, loops, and cogirth.
Right, so the next step is figuring out how to actually count those Schubert matroids. How do we do that?
So there's a formula for that. It's theorem 3.7 in the paper. It tells you how many Schubert matroids there are on a ground set, $none with a given rank, number of loops, and cogirth. You have to sum over certain subsets of the ground set and then calculate multinomial coefficients based on those subsets.
Multinomial coefficients, they seem to be everywhere in this. Why are they so important here?
Oh, they're essential in combinatorics for counting combinations and arrangements. So here, they help us count all the different ways to put together Schubert matroids with the properties we want. Remember, the permutation and the choice of the subset LR determine those loops and the cogirth.
So we've got this formula for counting Schubert matroids, but how does that connect back to those Chow polynomial coefficients? This is where it all comes together, right?
Exactly. This is like the heart of Ferroni's theorem. It says that the coefficient of a term in the Chow polynomial of a uniform matroid, it's equal to the number of Schubert matroids with a specific rank, number of loops, and cogirth.
So by using that counting formula, we can directly calculate the coefficients in the Chow polynomial. We're turning something abstract into something you can count.
That's it. It's pretty cool how combinatorics can help us understand those algebraic structures. The paper even gives a specific equation, it's equation 3.5, that shows how this counting works.
Can you tell me a bit more about that equation? What does it tell us?
So equation 3.5, it's the core of the counting argument. We sum over certain subsets of the ground set, and for each one, we count how many different Schubert matroids we can make using that subset.
So we break down the counting problem by looking at different subsets. But how do we know how many Schubert matroids come from each subset?
We look at all the possible permutations of that subset. Remember, the permutation affects the loops and cogirth of the Schubert matroid.
It really seems like permutations are the key to all of this. They change the ground set, and that changes the structure of the Schubert matroids, and then that changes the coefficients in the Chow polynomial.
You got it. Permutations are the bridge between all these different ideas. They're all about rearranging and ordering, which is important for both Schubert matroids and those Chow polynomials.
Wow, we've gone through a lot. The structure of Schubert matroids, how to count them, and how that connects to the coefficients in those Chow polynomials for uniform matroids. It's amazing how it's all connected.
It really shows how elegant math can be, and this is just the beginning. Ferroni's work opens up so many possibilities for understanding matroids and their properties.
I'm definitely curious. What are some of the directions that researchers are excited about?
Yeah, it's crazy. Who would have thought that just counting some Schubert matroids would give us the secrets to these polynomials?
It's like having a cheat sheet for some super complicated math problem. So you said that Ferroni's work could lead to some cool new research. What are some of the things that mathematicians are looking into?
Well, one big thing is seeing if these connections also exist for other types of matroids, not just the uniform ones. Remember, there's a whole world of matroids out there.
Right, like uniform matroids are just one type.
Yeah.
What about graphic matroids, transversal matroids, or oriented matroids? I mean, could we find similar connections for them?
That's the million-dollar question. If we could, it would change how we think about those matroids and what they can do.
It's like we found this map to a whole new area of math, and we're ready to explore it.
Exactly. And then there's those chronologies we talked about.
Right, the things that add in that extra Q parameter.
Yeah.
Could Ferroni's theorem work for chronologies of uniform matroids?
That's what everyone's trying to figure out. I mean, if there's a connection between the coefficients of some chronologue of the Chow polynomial and those Schubert matroids, that would be huge.
Like finding a secret room in a hidden mansion or something.
Yeah. Ferroni's work is more than just one theorem. It's like a starting point for all sorts of new research on matroids.
This deep dive has been amazing. We went from Chow polynomials and uniform matroids to Schubert matroids, all these combinatorial arguments, and then even those chronologues.
And it all comes back to this idea. The coolest stuff in math often comes from making connections between things that seem totally different at first.
This deep dive has definitely shown that. It makes you wonder what other mathematical treasures are out there.
For sure. And we want you, the listener, to be a part of this journey. Go explore those matroids, see what you can discover. You might be the one to find the next big connection.
It's a never-ending adventure. Well, that wraps up another deep dive. We've seen some incredible mathematical insights today and hopefully sparked your curiosity to keep exploring. Until next time. Welcome back to the deep dive. This time, we're going to be tackling uniform matroids.
Oh, nice.
Yeah, and their Chow polynomials.
Very cool.
And we've got a paper by Elena Hoster to guide us.
That's a good one.
Yeah, and believe me, this is where things get really, really interesting.
I believe it.
Yeah, it's not just about, defining these polynomials.
Right.
It's about uncovering their hidden depths and their connections to Schubert matroids, and even like how to actually calculate them.
Yeah, the calculation part is really cool. What I really liked about her work was that she provided a concrete interpretation for the coefficients of these polynomials, which was something that was only conjectured before. So it's like she found this Rosetta Stone that just unlocks this whole new level of understanding in the field.
Exactly. And she doesn't stop there. She gives us not one, but 3 different ways to express the Chow polynomial.
Oh, wow.
Each offering a different perspective on its structure.
Okay.
But before we get ahead of ourselves, let's make sure we're all on the same page. Can you give us a quick refresher on uniform matroids and what these Chow polynomials represent?
Sure. A uniform matroid, denoted as U sub ken sub, is a matroid on a ground set of n elements where every subset of size k is a basis. You can think of it like choosing committees of exactly k members from a group of n people.
So it's about equal representation, every combination of k elements being equally valid.
Exactly. Now, the Chow polynomial of a matroid and its close cousin, the augmented Chow polynomial, are polynomials in a variable usually denoted as x. And these polynomials essentially capture information about the independent sets of the matroid and their relationships.
Okay, so they're not just some random polynomials. They encode valuable information about the structure of the matroid.
Precisely. And what's particularly interesting is that the coefficients of these polynomials often have combinatorial interpretations. That is, they can be understood as counting certain combinatorial objects related to the matroid. This is where Ferroni's conjecture comes in. Ferroni proposed that there should be a precise combinatorial formula for the Chow and augmented Chow polynomials when you're dealing with uniform matroids.
It's like he suspected there was a hidden code within these polynomials, a code that could reveal even deeper secrets about uniform matroids.
Exactly. And Hoster's paper, in a sense, cracks that code. She proves Ferroni's conjecture and provides 3 explicit formulas for both the Chow polynomial and the augmented Chow polynomial of a uniform matroid.
Okay, so let's dive into those formulas, starting with the Chow polynomial of a uniform matroid. What's the first formula Hoster gives us and what makes it special?
The first formula is quite elegant. It utilizes subsets of the set 1, 2, deutopsis. It looks like this. Sum I, subset 1 $, 1 $, $1 x, 1 OK.
Okay, let me make sure I understand this. We're summing over all subsets I of the set 1, 2 delta that contain the element 1. But what's this I in the binomial coefficient?
That's a clever notation. Hoster uses I represents the multi-set of consecutive differences between elements in I. For example, if I 1, 3, 5, then I would be 2, 2, since the differences are 3, 1, 2, and 5, 3 equals 2. And the binomial coefficient is then a multinomial coefficient. In our example, it would be n choose 2, 2, which expands to n 2.2 and the TELF 4.
That makes sense. So each term in this formula corresponds to a specific subset, and the multinomial coefficient captures something about the spacing between the elements in that subset.
Precisely. It's like each subset contributes a weighted term to the polynomial, and the weight is determined by the arrangement of its elements.
That's a great way to visualize it. Okay, so that's the first formula. What about the other 2 formulas for the Chow polynomial? How do they differ from this one?
The second and third formulas delve into the realm of permutations. Instead of subsets, they use permutations of sets like 1, 2, an, or 1, 2, daute to express the Chow polynomial.
Interesting. So we're shifting from subsets to ordered arrangements of elements. Can you elaborate on how these permutation-based formulas work? What do they look like?
The second formula focuses on permutations of 1 to nm with no consecutive descents. A descent in a permutation is simply a position where the following number is smaller than the current one. The formula involves summing over specific types of these permutations and uses binomial coefficients to determine the contribution of each permutation to the polynomial.
So it's like we're filtering out certain permutations based on their descent pattern and using those filtered permutations to build the Chow polynomial.
Exactly. Now, the third formula, while also utilizing permutations, takes a slightly different approach. It specifically examines permutations of the set 1, 2, k, and relates them to binomial coefficients based on their cycle structure.
Wait, cycle structure. Can you explain that a bit further?
Imagine writing a permutation in cycle notation. For instance, the permutation 1, 3, 2 can be written as 1, 2, 3, indicating that 1 maps to itself, 2 maps to 3, and 3 maps to 2. The cycle structure refers to the length of these cycles. In this case, we have a 1 cycle and a 2 cycle.
Ah, I see. So this third formula is taking into account how the permutation shuffles the elements in a cyclic manner.
Precisely. And what's remarkable is that despite their different forms, all 3 of these formulas ultimately lead to the same Chow polynomial for a given uniform matroid.
That's pretty amazing. Having multiple representations of the same mathematical object can be incredibly powerful. It's like having different tools in your toolbox, each suited for a particular task.
I agree. It's like viewing a sculpture from different angles, each perspective revealing a different nuance of its form.
Okay, so we've got these three formulas for the Chow polynomial.
Yeah.
How does Hoster use them to actually prove Ferroni's conjecture? This is where things start to get really interesting, right?
Yeah, this is where the magic of Schubert matroids comes in. These fascinating objects provide the key to unlocking the combinatorial interpretation of the Chow polynomial's coefficients.
Okay, Schubert matroids. I've heard the name, but honestly, they sound a bit intimidating. Can you break them down for us? How are they connected to the Chow polynomial?
Absolutely. A Schubert matroid, denoted as subi, sub, is defined by a subset I of the set n equals 1, 2, n, and a permutation of n. And the way it works is that a subset J of n with the same size as I is considered a basis of subi, sub if and only if the elements of I are less than or equal to the elements of J when arranged according to the order determined by the permutation.
So it's like the permutation shuffles the elements of n, and that affects which subsets we're allowed to choose as bases?
Precisely. The permutation introduces a specific ordering, and that ordering dictates the structure of the Schubert matroid. Now, the connection to the Chow polynomial emerges when we consider the coefficients of the first formula we discussed earlier. Remember those multinomial coefficients based on the consecutive differences in subsets?
Yeah.
It turns out those coefficients are counting Schubert matroids with specific properties.
Wait, really? So those seemingly abstract coefficients are actually telling us something very concrete about the structure of these special matroids.
Exactly. Halster proves a crucial theorem, Theorem 3.7 in her paper, that establishes this connection. This theorem states that the number of Schubert matroids on the ground set n with a rank m, L loops, and a cogirth of n plus 1k is given by a specific sum of multinomial coefficients.
Hold on, let's unpack that. We need to define loops and cogirth first.
You're absolutely right. A loop in a matroid is an element that's not included in any basis. It's like a lone wolf independent of all the other elements, and the cogirth is the size of the smallest circuit in the dual matroid. Think of it as a measure of how interconnected the elements are.
Okay, so a high cogirth means the elements are loosely connected, and a low cogirth means they're tightly knit.
Precisely. Now, going back to the theorem, the sum in the formula runs over particular subsets of L plus 1, L plus 2, k, and for each subset, we calculate a multinomial coefficient based on the consecutive differences between the elements, just like in the first formula for the Chow polynomial.
Ah, I see where this is going. So the conditions on the rank loops and cogirth in this theorem are somehow mirroring the conditions in the first formula for the Chow polynomial.
Exactly. When you carefully analyze those conditions, they perfectly align. The rank corresponds to the size of the subsets. We're considering the number of loops restricts the starting point of our subsets, and the cogirth links to the differences between consecutive elements.
So it's like two separate paths converging on the same destination. We have this theorem about counting Schubert matroids, and we have this formula for the Chow polynomial, and they turn out to be describing the same thing.
Precisely. And that's how Hoster proves Ferroni's conjecture. By establishing this connection, she demonstrates that the coefficients in the Chow polynomial, those multinomial coefficients, are actually counting Schubert matroids with specific properties. She then extends this argument to the augmented Chow polynomial as well, showing a similar connection between its coefficients and Schubert matroids.
That's an incredibly elegant proof. It's amazing how she brought these seemingly disparate concepts together. What about those other formulas for the Chow polynomial, the ones based on permutations? Do they also tie into this proof somehow?
They offer alternative perspectives and computational tools, but they're not directly involved in the proof itself. Those formulas, the ones based on permutations and their descents, are actually derived from the gamma expansion of the Chow polynomial, a concept introduced in a paper by Stump.
Okay, so they enrich our understanding of the Chow polynomial by connecting it to different combinatorial objects, even though they're not central to Hoster's main proof.
Exactly. It's like having multiple maps of the same territory, each highlighting different features.
So we've explored these three fascinating formulas for the Chow polynomial, delved into the world of Schubert matroids, and seen how Hoster uses them to prove Ferroni's conjecture. It's really remarkable how much depth there is to these seemingly simple polynomials.
It truly is. And what's even more exciting is that this is just the tip of the iceberg. There's still so much to explore and discover in this area.
That's what makes mathematics so captivating. There's always another layer to peel back, another connection to uncover. But before we get lost in the vastness of it all, I think it would be helpful to ground ourselves with some concrete examples. Can we look at some specific cases of uniform matroids and see how these formulas play out in practice?
Absolutely. Examining specific cases can bring clarity and reveal some surprising connections to other familiar concepts. Let's consider, for instance, uniform matroids, where the rank is very close to the size of the ground set, like U sub n1 sub, where we have n elements and are choosing subsets of size n1.
Okay, that sounds manageable. What happens to the Chow and augmented Chow polynomials in these cases?
In these cases, the polynomials simplify in interesting ways and reveal connections to other well-known polynomials and combinatorics. For example, the Chow polynomial of U sub n1 sub turns out to be closely related to the derangement polynomial, a polynomial that counts permutations with no fixed points. Specifically, if you multiply the Chow polynomial of U sub n1 sub by x, you get the derangement polynomial of order n.
Wow, that's a surprising link. So the Chow polynomial, which we initially defined using multinomial coefficients and Schubert matroids, suddenly pops up in the context of derangements.
Yes, and it doesn't stop there. The augmented Chow polynomial of U sub n1 sub is directly related to the Eulerian polynomial, another important polynomial in combinatorics that counts permutations based on their number of descents. In fact, the augmented Chow polynomial of U sub n1 sub is precisely the Eulerian polynomial of order n.
So by looking at these special cases, we're uncovering hidden connections between seemingly unrelated concepts. It's like different parts of the mathematical landscape are intertwined in unexpected ways.
Exactly. These connections highlight the beauty and unity of mathematics, showing how seemingly different concepts can be linked through these elegant polynomials.
This deep dive has been incredibly insightful. We've explored uniform matroids, their Chow and augmented Chow polynomials, the connection to Schubert matroids, and even touched upon other fascinating polynomials like the derangement and Eulerian polynomials. It's amazing how much we've covered. But I think we are just getting warmed up. There's so much more to explore, and I'm especially interested in delving deeper into the connection between these polynomials and permutations. What do you think? Ready for round two?
Absolutely. Let's dive deeper into that connection with permutations. It's like we've decoded one layer of the puzzle with Schubert matroids.
Yeah.
But there's another layer hiding beneath, just waiting to be deciphered using permutations.
So where do we even begin? We've seen hints of a connection with derangements and Eulerian numbers.
Right.
But is there a more general framework for understanding these polynomials in terms of permutations?
That's the million-dollar question. While we haven't cracked the code completely, there are some intriguing avenues to explore. One approach involves looking at the cycle structure of permutations. Remember how that third formula for the Chow polynomial used the cycle structure of permutations of 1 2-way?
Right. It considered how the permutation shuffles the elements in cycles.
Exactly. Well, it turns out that the cycle structure of permutations is intimately related to other combinatorial concepts like partitions and Stirling numbers.
Wait, partitions? As in dividing a number into smaller parts. How does that tie into all of this?
Think of it this way. The cycle structure of a permutation essentially partitions the set 1, 2, Fei Wei into disjoint cycles. For example, the permutation 1, 3, 2, 4, 5 partitions the set 1, 2, 3, 4, 5 into the cycles 1, 3, 2, and 4, 5.
Ah, I see the connection.
Yeah.
So we can think of each permutation as inducing a specific partition of the set.
Precisely. And what's interesting is that certain types of partitions are counted by Stirling numbers. These numbers pop up all over combinatorics, and they have connections to polynomials, generating functions, and all sorts of fascinating things.
So it's like we're building a bridge between the world of permutations and the world of partitions and Stirling numbers. And somewhere along that bridge, we might find the key to understanding the Chow polynomial in terms of permutations.
That's the hope. And there are some encouraging results in this direction. For instance, there are formulas that relate the Stirling numbers of the first kind to the coefficients of the Chow polynomial for certain types of matroids, though not specifically for uniform matroids in general.
So there's a trail to follow, even if we haven't reached the destination yet.
Exactly. Another approach involves looking at the descent structure of permutations, which we've already encountered in those permutation-based formulas for the Chow polynomial.
Right. Those formulas focused on permutations with specific descent patterns.
Well, it turns out that descents in permutations are also related to other combinatorial objects like peaks, valleys, and inversions, and these concepts in turn have connections to various polynomials and generating functions.
So it's like we're exploring different facets of permutations, looking for that one feature that will unlock the secrets of the Chow polynomial.
Precisely. It's an ongoing quest, and while a complete and general interpretation of the Chow polynomial's coefficients in terms of permutations remains elusive, the journey itself is full of fascinating discoveries.
It's a reminder that mathematics is not just about finding answers. It's about the thrill of the chase, the excitement of uncovering hidden connections, and the sheer beauty of the patterns that emerge along the way.
I couldn't have said it better myself.
So to our listeners, I say this: keep exploring the world of permutations. Keep digging into those connections with partitions and Stirling numbers, and keep that sense of wonder alive. Who knows, maybe you'll be the one to finally crack the code and reveal the full permutation-based story hidden within the Chow polynomial. And until next time, happy deep diving.